All right, here we're looking at the 4.5 guided notes. These notes are writing function rules. And when we try and write a function rule, we want to basically take the given scenario. So there's going to be some real world scenario that they're going to give us, and we want to be able to write a function rule given that scenario. And as far as making a linear rule, these are some of the key components that we need to look for. First of all, we need to establish what our independent variable is, and this is usually this is usually our x value, and most often this is going to be time. And our dependent variable, again, this is usually our y value. And this is some sort of quantity. So I'm going to say quantity. So this is some sort of, some sort of like meters or something measurable usually. And then we want to figure out how much is added when the independent variable increases by 1 unit. So, usually this is time. So, in every minute, the balloon fills up by, you know, whatever volume. That's a terrible example, but this is some sort of change here. So I'm going to say I'm gonna call this is some sort of a change. Something is changing here. And then the initial value of the dependent variable. So at x equals 0, what is my y value? So this is for our initial value. We really want to know, like, what's our starting point? Where do we jump off at? So let's try this out and let's see if we can figure this out. The first example. A landfill has 50,000 tons of waste. Each month it accumulates an average of 420 more tons of waste. What is a function rule that represents the total amount of waste after m months? So, first thing I want to take a look at is here. Here we have months, and they even gave us a variable for it. So here our independent variable is m, and this stands for months. And again, this is usually time. So that's kind of one of the things, the characteristics I'm looking for. Now my dependent variable, well, what are we looking for? Waste. So my dependent variable, waste, so I'm going to call that W. This stands for waste. Now, what is my change? For every 1 unit well, here we're looking at months. So after 1 month, what happens? We add 420 tons. So my change is 420 tons per month. But I don't really need to keep that in my. I want to see that so we understand it, but this isn't something that we need to necessarily write inside the rule or the equation itself. So, for the tons per month, that's just so we know and understand how much is added and how often it's added. And then our initial value, well, it starts off with 50,000 tons, so my initial value is 50,000. And now we can write our equation. W, which is our dependent variable, so W, which depends on M in this instance, equals, now this is how we put these together. It's going to be our change times our variable, so it's going to be 420 times M plus our initial value here, which our initial value is 50,000. So note, there's something really, really, really interesting that happens here. We can now see that our our dependent variable equals whatever our change is, and that I'm going to make that delta here. Note, little Greek delta, it's a little small triangle. This stands for change. So change times, and now I'm going to write this as a reminder, independent, so independent variable plus our initial value. And this would make sense, right? If our independent variable is 0, then our dependent variable has our initial value, right? Because 0 times anything is going to give us 0, so 0 plus initial value, that would tell us what happens at the very beginning here. So think about this here as one way of writing these rules, or a way of thinking about how to write these function rules when it comes to linear functions. Oh, excuse me. All right, so let's try the next one. A helicopter hovers at 40 feet above the ground. Excuse me. Then the helicopter climbs at a rate of 21 feet per second. Write a rule that represents a helicopter's height, h, above the ground as a function of time, t. What is a helicopter's height after 45 seconds? Okay, so here, again, our independent variable gives it here as a function of time. So t, which stands for time. Yikes. I guess we can see that it's time. And our dependent variable here is h. h depends on time. So our height depends on how long we have been flying. Our change, well, our change is this rate, 21 feet per second. So this is, we have 21 feet per second. Now we could write that in, but I just want to make sure we collect all of our data first. What's our initial value in all of this? Well, it starts at 40 feet above the ground, so our initial value is 40 feet. So now we could write our equation, h equals 21 times t plus 40. And then it says, what's the helicopter's height after 45 seconds? Well, 45 seconds is time, so I will replace my t value with 45. So I say, here I can say, h equals 21 times 45 plus 40, which I don't know right off the top of my head, but that's okay. We have calculators for these things. Ooh, 945, and then we need to add 40 more feet to that. Plus 40, right? And we get 985. So this, my height, wait, what did we say it was? 985. 985. And now we want to make sure we leave our units. So we want to say the height is in feet. 985 feet. So hopefully we can start to see this pattern develop when we write these function rules, and hopefully we can see how to take a look at things that are linear and start writing these linear functions given these rules.